Okay, so again, we consider a regular stem Liouville problem on finite cross interval AB. So it consists of a homogeneous second-order differential equation. All right, and two separated boundary conditions. All right, so we rewrite the ODE. Okay, and so we have px y prime minus qx y is equal to lambda x and y. Okay. And because for a regular stem Liouville problem, the function of x is a positive function, so we may divide the function of x. Okay, so we have 1 of x and minus p of x y prime and prime minus q of x y, okay, equal to lambda of y. Okay. So when we write it, we define a linear transformation. Okay, called L from V. V is the vector subspace of the L2 space we describe. So V is the subspace we described on Tuesday. Okay, so such that as L of U. Okay, so for every U in V, so for every function in V, L of U becomes to a function in L2, so which is U prime, okay, and minus Q of X, U. Okay. Now, as we know, U is continuous differentiable, so U prime exists, all right? And we know U prime, we also assume U prime is absolutely continuous. So U double prime exists, okay, for almost all x on the finite cross interval. And we also assume U double prime is L2 in L2. So that the whole thing, so this is a function. And so this function is also in L2 space. So that's why after this linear transformation, this function is in L2. Okay? Because U is in V, right? It's in V. So any questions? Okay, and so this which is called regular stem-Liouville operator. Okay. So it's added with the with a regular stem-Liouville problem. On AB. Okay. Right. So so in here, because so this linear transformation is from such a regular stem-Liouville problem. So we know R of x is a continuous positive function. Q of x is a continuous function. P of x is a continuous positive function. And the P prime of x is a continuous function. Okay? So we all know these problems. Okay. And so remarks. To justify that 1 LU is in L2 space. Okay, so first of all, you have to justify after this this transformation. This is a function which is square integrable. Okay, the first one. Second, that U is linear, i.e. L alpha U plus beta V is equal to alpha LU plus beta LV for all UV in capital V and alpha beta in C. Okay. Maybe I write the following to okay, so you have to justify that this function for each U in the vector subspace capital V, this is indeed in L2. Okay, and second, that L is really a linear transformation, so you have to justify this linearity. Okay. Okay, and so now, so when we define such a linear operator, you will see that which is such a linear transformation. L, a regular term, there will be a problem. Okay, on AB becomes an eigenvalue problem. L U equal to lambda U on the complex vector space V over complex semi inner. Oh, okay. V. All right. So you see here. So you can see here, the left-hand side, when you compare with this, the left-hand side actually is L of Y. Okay? So a solution, all right, Y of a regular stem Liouville problem, okay, is actually a solution of this eigen problem. Okay. So an eigen problem is that for a linear operator such that we have this relationship. So it's called an eigen value problem. Okay. All right. So lambda is an eigenvalue, and U would be for any non-zero. U will be an eigenfunction. Okay. Okay, so now we will investigate the solution. All right, so we actually turn, all right, a regular stem Liouville problem to eigenvalue problems in a vector space V. Any questions? I know you will study eigenvalue problem at least in the second half of the linear algebra course. Okay. So, but such an equation is about the eigenequation. All right. Now I will state an important theorem. A stem Liouville operator. So a regular, so we can see a regular stem Liouville operator L. It's self-adjoint. On V with respect to the weighting function R of X All right. So what do we mean self-adjoint? That is for any u v in the vector space. So for any functions u and v in the vector space capital V, the inner product of when you transform u by L, okay, and you check the inner semi-inner product, all right, of L of u and v, okay, with respect to the weighting function R. Then the result will be equal to, all right, you transform V instead of U, okay? And leave U without any transformation, all right, and R. So which means that, under this inner product, the operation of L can be act on either U or V, okay, without change the result. This property is called self-adjoint property, okay. So if you rewrite because inner product has been defined in terms of definite integral, so we know this inner product is of x LU of x and the v of bar, okay. So this is the inner product with respect to the weighting function R at the left-hand side. And for the right-hand side, this would be u of x and L v bar dx. Okay? Okay. All right, so this is an important property for regular stimuli of your operator defined here. Okay, so now I give proof. So we are going to prove the equality of these two definite integrals. So let's consider the definite integral at the left-hand side. Okay, so that is the case. Now, and we look at this transformed function. See, it has two terms, right? So we will have so right after multiply R of x, right? We have minus P of x. Okay, and the u prime of x and the prime. Okay, minus q of x and the u of x. Okay, and the v of x bar. Okay, and so we have two terms. We have P of x, u prime of x prime, and the v bar x dx minus AB and q of x, u of x, v of x bar dx. All right. Okay. Okay, and so we have minus P of x, U prime of x, V bar of x, A to B, by integration by parts. So now we have AB and the P of x, U prime of x, and V prime of x bar dx minus AB, Q of x, and U of x, and V dx. Okay? So this is by integration by parts. All right. So integration by parts is here. Okay, and we okay, and similarly, the integral, okay, in the right hand side, okay, and again, U of x. Now we look at the transform the v. Okay, and we still have this the term in the denominator. So, and r is positive, so it's real. So under the conjugate sign, right, it will not change, right, because it's real. So that the denominator can be cancelled without the weighting function of x. And so we have minus P of x and V prime of x prime minus Q of x and the V of x, and take the bar, okay, and d of x. Okay, and now we have two terms. So we have AB and minus P of x and V bar prime x and prime and the U of x, D of x minus AB and Q of x, U of x, and the V of x bar dx. Okay. And the reason is Q and P are real value functions. Okay, so they are real value functions. Only U, V are complex valued function. So we can write it in this way. Okay. Any questions? And again, by integration by parts. So here we have minus. So we have minus P of x and U of x, V prime of x, and AB plus AB, and P of x, U of x, and V prime x. Oh. Yeah. Okay. U prime. Okay. X and dx. Yeah. Okay. And the minus AB Q of x, U of x, and the V bar of x. Yes. Again by integration by parts. Okay. And so we compare that these two final result here. You see that these two terms are the same, right? And also the middle term, they have the same middle terms here. Okay? The same middle term. All right. And so that's okay. So when we take the difference, okay? So when we take the difference of these two integrals, we can cancel these two terms, okay? And so we have P of x, okay? We have P of x, and U of x, V bar prime of x, minus U prime of x, and U bar x evaluate at these two boundary points. Okay? So you look at, okay. All right, and this equation okay. So this equation is called Lagrange's identity. Okay, it's called Lagrange identity. Now, remember, U and V are in capital V. Yeah, U and V are in capital V. And when we define this vector space, we say that any member, any function in capital V satisfy the two separated boundary condition. Right? Remember that? So now since UV is in capital V, U and V satisfy the two boundary conditions. in 11.5.2. So we can write it down. So that K1 UA plus K2 U prime A is 0. L1 UB plus L2 U prime B is 0. Okay? And also K1 VA plus K2 V prime A equal to 0. L1 VB plus L2 V prime B equal to 0. Right? So they satisfy two boundary conditions. And we can write these two linear equations in terms of matrix. So this is okay. So now when we these two equations, okay, see, have the same coefficient. And as we know, K1 and K2 cannot be both zeros, right? So at least one of them non-zero, okay? So that they can be rewrite in here, K1 and K2 equal to 0, and U A and U prime A, VA, V prime A. Okay, so that when we combine these two linear equations together, all right, so we have this one. So K1, K2 would be homogeneous. It would be a solution of this homogeneous linear systems. Okay, and the coefficients are UA, U prime A, VA, and B prime A. And similarly, we can consider these two equations together. Okay, you can see that they share with the same L1 and L2, and so we can write them as UB and U prime B, VB, V prime B, and this is L1, L2, and 0, 0. Okay. Now we have homogeneous linear system with non-trivial solution. So what is the consequence? When we have a non-trivial solution, then this matrix must be non-invertible. Why? If this matrix is invertible, then we have only trivial solution, right? Okay, right? So we have here things. All right, since these two solutions are non-trivial, so we call these two coefficient matrix UA, U prime A, VA, V prime A, and UB, U prime B, VB, V prime B are non-invertible. And have zero determinant. Okay, right? So this coefficient matrix are non-invertible, and so that their determinants should be 0. Okay, should be 0. Okay, so what is the determinant? So we have UA, V prime A. Oh, by the way, when we check, so when we take complex conjugate, okay, now, and so we take the complex conjugate. This is 0, right? So we take complex conjugate, we get the same relation. And we know K1 and K2 are real numbers. So it will not be affected when we take the complex conjugate on both sides. All right? And so we can take this one. So this is also true. Okay, and so the determinant UA and the V bar prime A minus U prime A and the V bar A is 0. And for this one, UB V bar prime B minus U prime B and V bar B is 0. Okay. All right. So now you look at here. When we evaluate, so with these two, so this implies that PA, okay, PA, or PB, PB of UB, and the V prime B minus U prime B, and V bar B, okay, minus PB, PA, U A, V prime A, minus U prime A, V bar A. Okay. Right, so look at the right-hand side of the Lagrange's identity, right? And the right-hand side is just the difference of these two terms, okay? So the first terms involve the boundary point B, right? And the second is involve the boundary point A. Okay, and from here we know this is just here. This is 0. The difference in the bracket is 0, and the difference in the bracket is 0. So this is 0. So that is PB 0 minus PA 0. So it's 0. Okay. Okay. So the right-hand side of the Lagrange's identity is 0. Okay. It's 0 because U and V are in capital V and satisfy boundary condition. All right. So now, AB P of X and the V bar X dx is equal to AB R of X. Sorry. okay, i.e. the inner product. Okay, so we prove that the regular stem Liouville operator L is a separate joint. Any questions? Right. So this is a non-trivial result. Okay. It just say that you have some symmetry of when you acting when you use the regular stem Liouville operator L to acting on UR on V, you will get the same result. Okay. Any questions? Okay. Now, we will show that eigenvalue, right, of a regular stem Liouville operator L are non-degenerate, i.e. there is a unique eigenfunction up to a constant. Okay. So, which says that if lambda is an eigenvalue, means that this eigenequation has a non-trivial solution. Okay, so because if you put u to be 0, then and for any lambda, you have a trivial solution which is 0. Okay, no problem with that. But when you have a non-trivial solution, means u not equal to 0. Okay, not equal to 0. Then then we have eigenvalue and corresponding eigenfunctions. And the theorem says that once you have an eigenfunction corresponding to an eigenvalue, then this eigenfunction is unique up to a constant. Because other eigenfunction will be proportional to the first one you get. Okay, and so we will give a proof for that. So we let y1, y2 be eigenfunctions. Okay, corresponding to a given eigenvalue lambda. All right, so then L of y1 is equal to lambda y1. Okay, and L of y2 is equal to lambda y2. Okay, because they are also associated with the same eigenvalue lambda. Okay. All right, so now we multiply the first equation by y2. So y2 L y1 minus y1 L y2. Okay, so you multiply y2 in the first equation on both sides. You multiply y1 on both sides and take the difference. Then you know this is lambda y2 y1 minus lambda y1 y2. So they are 0. Okay? In V. In L2. Okay. Okay, so they are 0 functions. Okay. And now we look at which implies that y2 times Rx, and so we have minus P of x y1 prime minus Q of x y1. Okay, and then minus y2 times Rx P of x. This is y1, sorry. y2 prime minus Q of x y2. Okay, so this is 0. Okay, by the definition of the regular stem-Liouville operator L. So it now, because R of x is positive, so we can multiply R of x on both sides. Okay, so we can first multiply R of x to eliminate the denominator here. Okay, and when you do that, we have 4 terms. Okay, but for the second and the fourth terms, they can be cancelled to each other, right? Because the second term is minus Q of x y1 y2, right? And the first term is plus Q of x and y1 y2. So they can cancel each other. All right, and so we have, so what we have would be y2 minus, and here we have P of x q1 double prime plus P prime of x y1 prime. Okay, and here we have plus y1 and the P of x y2 double prime plus P prime x and y2 prime equal to 0. Okay. All right, and so when we combine P of x and P prime x together, we know this is P of x and P of here. Okay, maybe right here, P prime of x, P prime of x, and P prime of x and y1, y2 prime minus y1 prime, y2 plus P of x. P of x we have y1, y2 to the prime minus y1 to the prime, y2 equal to 0. Okay, so we combine terms with the same factor of P prime x and the same factor of P of x there. Okay, and so this term can be written to be P of x, y1, y2 prime minus y1 prime, y2, and together equal to 0. Okay. Yep. So we just by some manipulation. Okay. Okay. The reason is when you go back, right, the derivative of this product is equal to the derivative of P times this term, right? Plus P of x times the derivative of this difference. But the derivative of difference is equal to this term. Why? Because there are two terms cancel to each other. So you can see you have y1, y2 prime prime minus y1 prime, y2 prime. Okay? Because the derivative of this difference has 4 terms. Okay, 1, 2, 3, 4. But these 2 terms can cancel each other. So that finally you have to give the difference here. All right, so you have okay, so the difference is here is 0. So when you integrate, so this is the derivative of that. So that implies that P of x, y1, y2 prime minus y2 prime, y2 is a constant C. Okay, for all x in AB. Okay, and what is this? This is so it's constant for all x in this finite cross interval. And recall recall the Wronskian of two function y1 and the y2 x here is the determinant of y1, y2, y1 prime, and y2 prime. Okay, so this is the Wronskian of two functions. And so this is the determinant, right? And so this is y1, y2 prime minus y1 prime and y2. All right, so this identity is about a description of the Wronskian. Right? And okay, and since both y1 and y2, okay, because they are y1 and y2 are functions in V, so y1 and y2 satisfy boundary conditions. Boundary condition at x equal to a in 11.5.2, right? So y1, y2 satisfy the boundary condition, right? So satisfy these boundary conditions. All right, so that means that k1 y1a plus k2 y1 prime a equals 0. K1 y2a plus k2 y2 prime a is equal to 0. And so that again, so this is y1a, y1a, y1 prime a, y2a, y2 prime a, and k1, k2 is equal to 0 real. So which, again, k1 and k2 are non-trivial. So this is a non-trivial solution. So the matrix is non-invertible again, right? And so this is implies the determinant. So this is implies the determinant of the matrix. So y1a, y1 prime a, y2a, and y2 prime a is 0. Okay, so that means that the Wronskian of y1, y2 at a is 0. Okay, so y1 and y2 satisfy boundary condition at a, implies that the Wronskian at a is 0. Okay, but as we know, this is just the Wronskian of y1 y2, right? So that PA, okay, and the Wronskian y1, y2 at a is C, which is 0. Okay, so this implies that C is 0. So this constant is 0. This constant is 0. Okay, so which shows that which shows that so P of x, the Wronskian y1, y2 of x is the 0 function for all x in AB. All right, so we show this result. But P of x is positive. So the Wronskian is 0 for all. Okay? Now, y1 and y2, okay? y1 and y2 are eigenfunctions. So y1 and y2 are solutions of a homogeneous second order ordinary differential equations. Okay? Remember that, right? When we construct. So this one corresponding to our homogeneous second order ordinary differential equation. Okay? So they are solutions. Okay, so we have corresponding to the same ODE. And their Wronskian is 0. Their Wronskian is 0 function. So this implies that y1 and y2 are linearly dependent. Okay, so they are linearly independent. Oh, maybe I'll say that. Now the Wronskian is 0 already. Now, since both y1 and y2 are solutions of a homogeneous linear second order ODE. Okay, so it's a solution of this a solution. Okay, with continuous and with continuous coefficient. On AB. Okay, now by the theory of ordinary differential equation, we know y1 and y2 are linearly dependent. Function on AB. So that y2 equal to c equal to alpha y1 equal to alpha y1 for some non-zero complex constant. Right, so this proves the theorem. Okay. Okay. So the theorem shows that if the y1, y2 are eigenfunctions corresponding to the same eigenvalue lambda, means that y1 and y2 satisfy these two eigenequations. And we show that y1 and y2 are proportional to each other. Okay, so that the corresponding eigenfunctions, okay, is unique up to a constant. This phenomenon is called non-degenerate. So when an eigenvalue is non-degenerate, means that the corresponding eigenvalues are proportional to the corresponding eigenfunctions are proportional to each other. Okay. Any questions? I believe you know this property. If you don't know, please raise your hand. Okay, good. Because that when we solve a second order ordinary differential equation, especially linear differential equations, we know that there are two independent solutions. Okay, and how do we check that two solutions are independent? You use Wronskian, right? Remember? So if the Wronskian is non-zero at a point, if it's non-zero at a point, then it will be non-zero for all points. Okay, and if the Wronskian is non-zero at any point, then these two functions must be linearly independent. Very strong. Okay, and also we have proof that if there is one point for the Wronskian to be zero, then the Wronskian will be zero for all points. It is very strong. Okay, in the theory of ordinary differential equation. Okay, right. So Wronskian is a very important tool to justify two solutions of a homogeneous linear second order equation to be linearly independent. So we can find two independent solutions, and then a general solution, will be a linear combination of these two independent solution plus a particular solution. Okay, this is the way we solve a second order linear differential equation. Okay. Okay, and the theorem basically use the idea of Wronskian, all right, to prove, all right, and it's natural. Why? Because y1 and y2 satisfy this homogeneous linear second order ODE. Okay, and with continuous coefficients. So you see, p of x, p prime of x, qx, rx, they are all continuous functions. Okay, and this is a linear ODE. Okay, this is a linear ODE. Okay. Even though the coefficient is not constant, the coefficients are functions, but they are continuous functions. Okay. Now, with the theorem 11.5.c, right? So basically, theorem 11.5.a and point B, they are two important properties of a regular Stim-Liouville operator. Okay. Now, a direct consequence is that of theorem 11.5.8 is that any eigenvalue of a regular Sturm-Liouville operator L, if exists, it's a real number. Okay, so when we want to know to find the eigenvalue of means that for any lambda such that this homogeneous second order ODE has non-trivial solution, we consider only real numbers, right? Because if because this is this theorem, okay? Because the eigenvalue, the corresponding eigenproblem is only real eigenvalue. And the proof is the direct consequence of of theorem 11.5.8. So now we assume that lambda is an eigenvalue of L, and U is an and U an eigenfunction in V corresponding to lambda, i.e. We have so we have L U equal to lambda U. Okay. So we suppose, all right, lambda is an eigenvalue, means that there exists a non-zero function satisfying the eigenequation. Okay, and the U is just an eigenfunction, right? So any eigenfunction should be non-zero. Okay. Now since L is self-adjoint, okay? So we just, as in theorem 11.5.8, we have so we have LU R is equal to U LU R. Okay, so we have this identity. Okay. All right, and because U is an eigenfunction, so this is lambda U R equal to U lambda U R here. Now, the semi inner product is linear for the first argument, so we have lambda U R. But the inner product is conjugate linear for the second argument, so we have lambda bar U R. Okay? Okay, and now since U is not zero, okay? Since it's not zero, so it's not zero, so the inner product is not zero. Okay. Remember, U is continuous because U has continuous, is continuous differentiable. So U itself is continuous, and so U cannot be equal to zero almost all x, right? And so that so U should not be equal to zero, and the inner product is non-zero. So this is implies that lambda is equal to lambda bar, because you can cancel them. Okay, and this implies that lambda is real. Okay. Any questions? Remember, Okay. So any u here is continuous function, okay, because it's in capital V. You know, we have 4 properties for any function in capital V, and so u is a continuous function, okay, and it is non-zero. So maybe I will say here. Maybe I write here. It's not equivalent to 0 at all, okay? Because the u has 0 inner product with itself if and only if u is equal to 0 almost for almost all x, which means that if and only if u is equivalent to 0. But because u is a non-zero eigenfunction, right? And u is continuous, so u is not equal to 0. All right, not equivalent to 0. Okay. Now, remember we took 2 examples of a regular stem-Liouville problem, okay? And in those 2 examples, we find that eigenvalues appear to be discrete. Remember that? To be discrete, right? So, so now we have the same question about for a regular, a general regular stem-Liouville problem. What are possible eigenvalues? All right, and so the theorem says that give an answer. The eigenvalues, okay, of a regular stem-Liouville operator form an infinite increasing sequence. So the eigenvalue are discrete, and it's an equation sequence, unbounded, basically. Okay, and the limit of lambda n when n goes to infinity is infinity. So this sequence is unbounded. Okay. So this gives us the answer about the existence of eigenvalues of an arbitrary regular stem-Liouville problems. All right. So when you are considering a regular stem-Liouville problems, it means that you have a stem-Liouville, a regular stem-Liouville differential equation with the 2 separated boundary conditions specified. Then the lambdas, the parameter, appeared in the differential equation such that the ODE has non-trivial solution. Okay, this lambda appear to be discrete and form increasing sequence. All right, and this eigenvalue will goes to infinity. right? As n goes infinity. Okay, so it's unbounded. Okay. Okay, and the from theorem 11.5.b, each eigenvalue is non-degenerate. So that means that for each eigenvalue lambda n, and from 1 to etc., we can select one corresponding, okay, so we can say one corresponding eigenfunctions, say phi n, okay. If you select other eigenfunctions, then they were proportional to each other, so you just take one, okay. So you just take one corresponding eigenfunctions, we call phi n, and to form an eigensystem. So an eigensystem okay, so an eigensystem consists of eigenfunctions, okay, and each of them is associated with different eigenvalues. Okay, so this is called an eigensystem. And this eigensystem consists of infinitely many functions. Okay. And note that each phi n, okay, is in V. So each phi n satisfies the four properties. Okay, when we define capital V. First, each phi n is continuous differentiable. Second, its derivative, phi n's derivative, is absolutely continuous, so that the second derivative of phi n exists for almost all x. Third, the second derivative of phi n is in L2, so the second derivative of phi n is square integrable. Fourth, each phi n satisfies the two separated boundary conditions. Is that clear? So this eigensystems has specified the property in B. Okay, because they are constructed, they are eigen functions. Okay, because we define the L on this vector space. And so we can show, now we can show that this eigenfunctions, because these eigenfunctions corresponding to different eigenvalues, and we will show that they are orthogonal to each other. Okay. So theorem 11.5.1. Orthogonality of an eigensystem. Okay, so we will show the orthogonality. Okay, so if phi 1 and phi 2 are two eigenfunctions of a regular Sturm-Liouville problem corresponding to distinct eigenvalues number 1 and the number 2 respectively. Okay, so suppose we pick up 2 eigenfunctions from this eigensystem corresponding to different eigenvalues. Then phi I, phi j, sorry. Phi I, phi j, lambda I, lambda j. Okay, so ij are different index. Okay. Then phi 1, phi I, and phi j, this inner product with weighting function r of x, phi ix, phi j x bar dx is equal to 0. So they are orthogonal to each other because the inner product of these 2 eigenfunctions is 0. Okay, so that okay, and the proof will be easier once we have previous discussions. Okay, the corresponding theorem in the textbook, I'm not sure that it gives you any proof. I'm not sure. Okay, but you can see that since L is self-adjoint, so it is a consequence of theorem 11.5.8 on V with respect to the weighting function of x. So we have the following result. When we apply this is regular stem-Liouville operator on phi I, and then compute the inner product with phi j with respect to the weighting function r, and we know that this is equal to applying L to phi j. Okay, so this is because L is the self-adjoint. Now, so that here, this is lambda I, phi I, and phi j. Okay, we have that. And the phi I here. Now, phi j is eigenfunction corresponding to eigenvalue lambda j. So you have lambda j, phi j here. Now by linearity, okay, so we have lambda I for the first argument, phi I. And by conjugate linearity, okay, so we have lambda j bar, phi I, phi j here. Now, we have shown that any eigenvalue is real. Okay, it's real. So this is implies that lambda I is lambda j, phi I, phi j, since lambda j is real. Okay, by theorem 11.5.c. So it's okay, and so lambda I minus lambda j times the inner product phi I, phi j is 0. Okay, but the difference is non-zero. So this the only thing is phi I, phi j, r is 0. Okay, so we prove this result. All right, so the orthogonality is a direct consequence that L is self-adjoint. Okay, because when L is self-adjoint, we know the eigenvalues are real. Okay, and we show that eigenfunctions corresponding to different eigenvalues are also orthogonal. Okay, so they are orthogonal to each other. So we have orthogonality. Now, an eigenfunction, okay, so an eigenfunction phi n, okay, corresponding to an eigenvalue lambda n of a regular Sturm Liouville problem is called normalized. Okay, with respect to the weighting function of x if the inner product of with itself is equal to 1. Okay, so that means that the length of phi n is equal to 1 with respect to the weighting function r of x. All right, so then phi n and from 1 to infinity is called an orthonormal eigensystem of the regular Sturm Liouville problem on AB. Okay, so we have now we have constructed, or at least we can construct an orthonormal eigensystem. Okay, eigensystem. Now for any square integrable function on AB, so f is a square integrable function. The series, now we can construct a series summation n from 1 to infinity Cn phi n of x, y, with the coefficient Cn to be the inner product of f and phi n with respect to R. Okay. Okay. So the coefficients are defined to be the inner product of f of the square integrable function and the eigen function phi n. Okay, so we have so this can be computed and we form series. Okay, so this series is called the regular generalized. So regular generalized Fourier series generated by f with respect to the eigensystem phi n. Okay, so this regular generalized Fourier series can be constructed for any square integrable function. Okay, because f is in L2 and phi is also in L2. Because phi, every eigenfunction are in capital V, and capital V is a vector subspace of L2 space. Okay. Okay. So this integral has finite value. Okay, and with the coefficient, we can construct this series. So such a series always exists for every square integrable function. Okay, and as the Fourier cosine series and the Fourier sine series we discussed before, you can see the collection of all sine functions. So sine nx or n from 1 to infinity. This system actually is an orthogonal eigensystem, right? Of a regular stem-Liouville problem in example 1, right? So in the first example, we already construct such an eigensystem consists of sine function. Okay, and in the second system, we construct cosine function. So cosine 0 x, cosine 1 x, cosine 2 x. Cosine 0 x is just equal to 1, right? So we have and they are corresponding. They are eigenfunctions of a regular stem-Liouville problem. Okay, and we also find the corresponding eigenvalues, right, by argument. Okay, by elementary argument. And here, what we construct is for general regular stem-Liouville problem. Okay, because there are many different regular stem-Liouville problems, and so for each such a problem, we construct an eigensystem. They are different to each other. Okay, and for each such eigensystem, we find that they are also normal. Okay, and the sense of orthogonality is we construct such an inner product, all right, with a weighting function R. Okay, so this is the reason why we have to go to construct inner product space. Okay, and it turns out such an inner product would be the weighted inner product. Okay, weighted by R of x. All right, weighted by R of x. All right, so we have orthogonality. And now once we have a series expansion, we have convergence and representation problem again, as we considered before. So finally, we have a theorem to say the representation. So it is the representation theorem of regular generalized Fourier series. Okay? Right, so we will say that let f be piecewise continuous, okay, on AB, and have a piecewise continuous derivative on AB. Okay, so for such a general class of functions, so f is piecewise continuous on AB, and have a piecewise continuous derivative on AB. Then 1. The generalized Fourier series, okay, summation n from 1 to infinity Cn phi n of x generated, right, by f with respect to an also normal eigensystem phi n of a regular Sturm Liouville problem on AB will converge. Okay, so we'll converge to the average of their left-hand and right-hand limit at each point x in the open interval. AB. Why just only open interval? Because these eigenfunctions, phi n, every eigenfunctions must satisfy the two separated boundary conditions. So the boundary conditions limited the behavior of the phi n's, because phi n's are in V. Okay, so they satisfy, and so that, for example, for cosine function, you know that at the 0, it's always 0. So the value of this series at the x equal to 0 is 0. But f may not be 0 when at an endpoint. Okay. All right, so we can't have a good convergence property at the two endpoints at A or B. Okay, but for this open interval, then every point, then this generalized Fourier series will converge to this one. So that if f is continuous at x at a point in this open interval, then this generalized Fourier series will converge to f of x. Okay, But the worst case goes to the half of these two limits. Okay. Now, at the endpoint, x equal to a, the regular generalized Fourier series summation converge to to the right-hand limit if k2 not equal to 0. Right? So if in k2 not equal to 0 in part A of 11.5.2, because there are two parts, right, for the boundary condition. So part A and to 0 if k2 is 0. Right? So when k2 is 0, we know that phi NA must be 0 for all. Okay, so this is to describe the convergence behavior of this generalized Fourier series. So if k2 is 0, remember what is k1, k2? Well, at A, because k1, we know k1 phi NA plus k2 phi n prime A equal to 0, right? So every eigenfunction satisfies the boundary condition at the endpoint A. So this is the boundary condition. Okay. And so if k2 equal to 0, which means that phi A must be 0 because k1 cannot be 0, right? So when k2 is 0, k1 cannot be 0. So which shows that phi NA is 0. So when phi NA is 0, then the sum at the x equals 0 must be 0. Okay, so this is why the Fourier series converges to 0. But when k2 is non-zero, okay, so the first derivative will evolve into the boundary condition, and in that case, the Fourier series will converge to the right-hand limit of f of x at A. So that would be a good situation to have. Okay, so this is for at the endpoint. Now at the endpoint, similarly at the endpoint x equal to b, okay, then the regular summation, so this regular generalized Fourier series, okay, converge to the left-hand limit of the function f at x equal to b if L2 is not equal to 0. All right, and to 0 if L2 is equal to 0. Once again, okay, and this is equal to, because of that, All right, so this is the boundary condition at the point endpoint B. Okay, so we have the similar behavior. So that is the second property. Okay. Now, so the first two is about pointwise convergence of the pointwise convergence, right, of the generalized Fourier series. How about the uniform convergence? So if f is also continuous, okay, on CD with A less than C less than D less than B, then the generalized Fourier series converges to F, okay, uniformly and absolutely. On CD. Okay, so for any finite closed interval within the open interval from A to B, when F is continuous in that finite closed interval, then this generalized Fourier series will converge to F uniformly and absolutely. Okay, and the rest two is about the endpoint behavior. So if F is also continuous, okay, on AB, AD with A less than D less than B, and F of A is 0 if K2 is 0, so that phi n A is 0. So if K2 is 0, then phi n A is 0. Okay, so in this case, then the generalized Fourier series will converge to F uniformly and absolutely on AD. Okay, so this is the situation that F is continuous on a finite interval including an endpoint. Okay, so the last one is or if F is also continuous on CB with A less than C less than B, and the F of B is equal to 0 if L2 is 0. So that phi n B is 0. Okay, so in this case, then the generalized Fourier series converges to F uniformly and absolutely on CB. Okay. So the theorem answers all the questions about convergence and the representations, okay, of the Fourier series. Okay. Okay. So basically, we have answered the questions about a regular stem-Liouville problem. Okay. So, any questions? Yeah. Okay, so I stop here.